Yeah, yeah. Sir, see it is.
Ah, yes, sir, started.
Sir
Oh,
started.
yes, yes. Now continue.
Okay. With great honor, once again, I welcome all the participants to the FDP. Now, I would like to briefly introduce today's speaker. Dr. Ibrar Jahan MA is an assistant professor in the Electronics and Communication Engineering Department, MS Institute of Technology, Bengaluru. She completed a BE degree in Medical Electronics from MS Ramaya Institute of Technology, Bengaluru. She completed her MTech in VLSI Design and Embedded System from UTL Technologies, VTU Extension Center, Bengaluru, and received PhD from VTU in Integrated Photonics. She has 21 years of teaching experience. She is a senior member of IEEE and an esteemed member of various executive committees, including IEEE Photonic Society Bangalore section, Prakash Bharati, and IEEE Sensor Council Bangalore section. She has published more than 25 research papers in national as well as international conferences and peer-reviewed journals. She has guided 6 PG scholars. She has given expert talk at various reputed institutions. She has received 3 times the Best Paper Award. She has served as reviewer in journals and conferences. She has received Best Project Award from DSC, AIC, and ITI Ayog, Bangalore, and KSCST, Bangalore. She has received Padma Shri Dr. S.K. Shivakumar Award 2022 for an innovative project from Karnataka Science and Technology Academy. She has won a Silver Award in INX International and Innovation Expo 2023. She is also the author of a textbook on basic electronics and semiconductor devices. She has received a grant of rupees 10 lakhs from IITI Drishti as a co-principal investigator. Once again, it's my pleasure to welcome you, ma'am, on behalf of management, principal, deans, HODs, and all the faculty members of the Oxford College of Engineering. Over to you, ma'am.
Thank you so much, ma'am, for that wonderful introduction of mine. And before I start my presentation, first of all, I want to thank all the members, the coordinators of today's presentation, especially Preeta ma'am, Manju Devi ma'am, and all the coordinators. So, ma'am, I want to share the slides. Shall I go ahead?
Yes, ma'am, you can share the.
Just tell me whether my slides are visible or not once I share this. My slides are visible, ma'am?
Yes, yes,
Yes,
it is
ma'am, it is
visible.
visible.
Make in
Ah,
presentation
then,
mode.
now it is presentation mode.
No, no, no,
Now, ma'am,
no.
not it.
It is not. Now it is in presentation mode. Now you
I
can
think it
start.
is slow. Yeah, yeah, it's a bit slow now. It's there, no, ma'am?
Yeah,
Presentation mode.
yeah,
Yeah.
yeah.
Okay. So, good morning once again to all of you. The outline of my presentation goes like this. Since the topic of today's discussion is grating structures for biosensing applications. So probably I'm going to cover about the basics of photonic integrated circuits, and then we're going to focus completely on the grating structures. And before moving on to the different types of grating structure, we can see what is the principle of grating, Bragg grating especially, and then again in waveguide and in fiber optic, how these grating type of sensors can be made and they can be used for different biosensing applications. So as I said, the outline of the presentation goes with the overview of photonics, followed by the grating principle and their application in biosensing. So coming to the introduction, as we all know, photonics basically involves with the science, which involves in the detection, the modulation, the manipulation and amplification of the light signal. So the field, I mean, I can say the study of photonics began in the year 1960 with the discovery of lasers. And then slowly the progress followed with the introduction of optical fibers for carrying the information, for carrying the data. This photonics is related to other domains like optomechanics, quantum optics, electro optics. So overall, I can say photonics is an all pervasive technology which allows the unlimited light travel, which is faster, I can say, compared to the electronic counterpart. Photonic technology is playing a vital role in healthcare industry. It is mainly focusing on low cost diagnosis, faster responses. I mean, like the usual method of identifying any disease, especially if I take the example of diabetes. So if a person want to know what are his sugar levels, whether he is a diabetic or not, probably he has to go to a lab, has to give his blood sample, and doctor will take a lot of time to find out the complete procedure, and maybe end of the day that person is getting the report. So the same thing, if it is transferred into a photonics technology, obviously the amount of time required to complete this entire process is very, very faster. So with this, the photonic technology has gained a lot of importance, especially in healthcare diagnosis. And not only that, it also involves invasive, non-invasive surgeries and invasive surgeries too, especially like endoscopy and all. If people want to know what is there inside the stomach, so they make use of this optical fiber based devices to know. In addition to that, these light based technology, they provide better response and faster response. They also helps in minimizing the side effect. There are no side effect when we use these type of devices. And as I said, the main focus is on the reduction of the cost and shorter response time. These optical sensing technology can recognize various biological species, chemicals, and they can also be used for identifying the nuclear threats and for homeland security. So, not only in sensing domain, this photonic technology is also gaining importance in domains like satellites, microwave sensors, and the new generation type of radars. So since I'm focusing completely on the biosensing application, let us see what exactly is a sensor and what are the different classification of sensors we have. So basically a sensor is an analytical tool, I can say, which detects and responds to certain physical or maybe external stimuli. And then it converts that parameter into a measurable and a quantifiable parameter or a signal. And these sensors, they allow the detection of specific analytes. And I can say any sensor in general consists of three parts. One is a recognition element, which mainly provides the specificity and the selectivity for a particular target. Then it has a transducer part, which converts a biomolecular or maybe a chemical reaction or interaction into a quantity which can be measured and quantified. And then it also has a signal processing part, because whenever we are doing certain capturing and measuring certain things, there is a probability of noise getting induced. Okay, so it also has signal processing part where the noise or the unwanted glitches can be removed and complete the required signal or parameter can be measured. So each application of these sensors, they require certain concentration of the analyte. It also requires certain time to complete the entire the procedure, and even certain time for the biosensor to be reused once again. So these sensors are classified into different groups, like one is optical based, acoustic based, and electrochemical based. So I'm not going to go into acoustic and electrochemical. My focus is going to be completely on optical based sensors. So optical sensors, they measure the variation in the light properties. So that variation can be in terms of wavelength or polarization or intensity, in order to detect certain biological analytes or maybe some chemicals or maybe gases. So these optical devices in general can be put into two categories, like label free based sensors and label based sensors. So what is the difference? In label-based sensors, it uses a special labeling to generate an optical signal, okay, to create the response. Whereas in label-free sensing, the detected signal is generated directly by the interaction between the measured analyte, I mean the analyte which we are going to measure, and the sensor. So this is a major difference between a label-free and label-based sensors. So coming to particularly the optical sensors, so these optical sensors, they can be fabricated, and in the absence of analyte, they also give a response, but it's not accurate. So whenever analyte or certain species, I can say chemicals, when it is put onto the sensor, definitely it produces a response. So here have taken a small example. When the surface of the structure is covered with a thin biolayer of molecules. The first structure you can see is just a structure, nothing is coated on top of the structure. And the same structure is coated with certain analyte or maybe dipped with certain analyte. So immediately there will be a change in the refractive index, and that will lead to a change in the response. That is the shift in the resonance peak. And this is mainly achieved because of the phenomena known as the evanescent field, which decays exponentially with the distance from the sample. So you can see the graph here. The first structure where there is no analyte coated on the structure, there is a particular response it is giving. The moment it is coated with certain analyte, due to a change in the refractive index or maybe due to the change in the wavelength or intensity, there is a shift in the wavelength. So looking at this waveform, easily we are able to identify whether any diseases are there or not, or the person is infected with certain infections or not. Now, coming to the integrated photonic circuits, as we all know, these integrated photonic circuit, they house in them both active and passive elements. I can say it's a quite mature technology, and even the size is very small. It's somewhere in nanometer or micrometer. And one major benefit of these integrated photonic circuits is the immune to EMI. And not only that, they also help us, they also has the advantage of point and distributed configuration. So you can see it's a substrate, integrated device on which various active and passive elements are embedded. So it is possible for us to come out with a very small fabricated device with many active and passive elements embedded on. And now coming to this silicon technology, what is this silicon photonic technology or silicon photonics? As we all know, silicon photonics is also known as silicon on insulator. It is, I can say, it's a semiconductor technology where the components are basically etched or patterned or fabricated in a standard 180 or 220 nanometer silicon layer. And then we place an insulating layer where the dimensions are somewhere around 1 to 3 micrometer. Then these silicon passive elements are formed basically initially with a few mask layers, either through partial or full silicon etching, and then later with multiple ion implantations. And coupling the light into and outside of the chip, that is, whenever I want to launch a light into these integrated circuits, we can make use of the couplers, where usually these couplers, they come with a very minimal losses of 1 dB per facet. And I can say the major benefit of SOI technology is its potential compatibility with the current CMOS fabrication process. So this allows us to have batch fabrication, and it will also lead to a smaller footprint area. In the sense, we can bring down the size of our sensors or our devices. And since I'm going to focus on the waveguide Bragg rating based devices for sensing application, it's essential for us to know the basic waveguide. So what exactly is a waveguide? What are the different classification of waveguide? What are the different types we have? And based on the light confinement, how they are classified and so on. Basically, a dielectric waveguide is a building block of any integrated photonic device. So here the optical energy is guided through the total internal reflections. So for this to happen, we have to make sure that the refractive index of the core is higher compared to the refractive index of the cladding. And for the light to confine in a waveguide, the condition of TIR, that is total internal reflection, is must. Along with that, since we are using soy-based platform or silicon on insulators, we usually make sure that the refractive index of the core is around 3.45 or maybe 3.4 or 3.5 around. And cladding, it is 1.45 with an operating wavelength of 1550 nanometer. And they have high index contrast, in the sense we can have many devices on a single wafer. So the density of the devices can be more. And these waveguides are classified based on the direction of the light confinement as 1D waveguide and 2D waveguide. Where in 1D waveguide, the light is confined in one dimensional only. Example, a simple slab waveguide. Whereas in 2D waveguide, the light is confined in two dimensions. It is also known as channel waveguide. So these are some of the basic designs, I can say, the different classification of 2D waveguides. Here it's known as a single mode structures because their dimensions are selected in such a way that they support only the single mode propagation. See, since we are talking about sensing application, we need to design, or we need to have the dimension of the devices in such a way that it supports only the single mode. If I am using them for communication or any other application, probably I can have multi-mode propagation. But since I'm focusing on the biosensor, so we need to choose, or we need to optimize the device dimension so that it supports only the single mode. And one more very good advantage they have is they can withstand the vibration and even the changes in the temperature. And it is also possible for us to control the guided wave. We can make them very compact and very light. And we can have even larger optical power density. As we said earlier, since it is compatible with CMOS technology, it is possible to have a mass production or maybe batch fabrication. So these are some of the examples of different types of 2D waveguides, where we have buried channel waveguide, strip waveguide, ridge waveguide, then we have rib waveguide, okay, and then we have diffused waveguide. So now let's come to the Bragg rating principle. Basically, a Bragg rating, it consists of a periodic medium. So I can say, if this is a waveguide, a simple waveguide, the gratings can be created inside the waveguide. Here in gratings, in Bragg ratings, a band of wavelengths are launched. I can say light is launched into the device, where light composed of multiple wavelengths. So when light is launched and when this light is going through the gratings, some of the wavelengths are transmitted and some wavelengths are coupled together and reflected back. Okay, so this is the basic principle on which this Bragg rating based devices they work. And here you can see that the light is launched in the Z direction. Here the interactions are in one dimensional depending upon the periodicity and the effective refractive index of these gratings. And because of that, a particular wavelength is reflected back and most of the wavelengths are transmitted. So this is due to, I can say, the coupling of the transmitted and the reflected wave, which results in a stronger reflected peak. Now, since a lot of this one electromagnetic equations are involved here, I have not taken all of them. Otherwise, the discussion will be focused only on the solution of these wave equation. So I have just taken the final equations here. Now, considering the first order diffraction and coupling of the forward and the backward propagated wave, here the propagation modes are same for both the waves. Only thing, the direction of propagations are different. I mean, it is opposite. With that, the grating equation, in general, the grating equation is given by n average is equal to sine of theta m, where theta m is at a particular angle, the light is launched into the device, okay, is equal to n incident, that is the average effective index and the effective index of the incident. That is the complete grating equation. And as I'm saying here, when the light is launched into the grating structure, some of the wavelengths are transmitted forward and some of the wavelengths are coupling back. I mean, they're coupled and they're reflected back. So with that, our grating equation, by inputting these two remaining equation, it can be reduced to lambda b is equal to an effective grating period. As I said, there are a lot of steps here to solve these equations. I have not put because of the time constraint. So we land up by solving all these electromagnetic equation with a final expression, which is lambda b equal to an effective grating period, which is known as the Bragg's condition or the Bragg's law, where lambda b is known as the Bragg's wavelength and effective is the total effective index, and grating period, this big lambda is the grating period of the pitch. So based on the whenever these sensors are subjected to certain responses like pressure or temperature, either due to the change in the effective index or maybe due to a change in the pitch, there will be a change in the center wavelength. So without any when the sensor is not exposed to any parameter, there will be a particular center wavelength, let's assume 15 nanometer. And when it is exposed to certain stimuli, then depending upon the grating period or there is a change in the effective index, even lambda b shifts. So from that, we can conclude what is the amount. I mean, based on the amount of shift, we are able to identify whether there is whether the sensor is responding or not. So lab on chip application, like how we have fiber Bragg rating sensor, in a similar way we have waveguide Bragg rating sensor. The problem here is FDG sensors, because of their size, we cannot use them for lab on chip applications. That's why whenever we are focusing on lab on chip kind of application, it's better to focus on waveguide based or integrated circuit based devices. As I said earlier also, it has a lot of benefits and it has brought a lot of revolution in the medical diagnostic field. These integrated sensors, they exhibit very good, excellent performance, I can say, to detect various analytes. They're also quite reliable and sensitive. The realization of the Bragg ratings on silicon on insulator waveguides, they offer the possibility for us to extend the functionality of these devices, and at the same time we can bring down their dimensions. And not only that, the optical confinement, the light optical confinement in these devices is very good, and even the losses associated with them is also minimal. Because it's possible for us to, since it's a high index contrast device, so it is possible for us to optimize the dimensions and make the amount of losses associated with the device lesser. So here, out of so many types, we have slot, we have ridge based, we have rib based. I am focusing on one type of waveguide Bragg rating device, that is rib waveguides. The reason why rib is, if you go to the literature and you review the papers or maybe read the papers, many people are focusing on the rib based grating structure. The reason is that in rib waveguide, it is easier for us to optimize the device dimension. And even from the fabrication point of view, it is easier to fabricate this rib based waveguide grating structure compared to the other type. And whenever we want to have a grating structures on the rib waveguide, we need to follow certain conditions here. Okay. So those conditions, like we have to make sure that our waveguide supports the single mode for sensing application. So we need to satisfy certain conditions, where those condition is given by this equation. It is known as the Sorev's equation, because he was the first person who came up with these concept, and he gave us like how the device dimension can be optimized so that it supports the single mode and even the losses associated are lesser, and it is easier also to fabricate the device. So we have these conditions here, where W by H, where W is nothing but the width of the waveguide and H is the total height. And small h, which is the slab height. In the next PPT, I'll show you the structure diagram, where from these equation, it is possible for us to determine the ratio R, where R is nothing but the ratio of slab height to the total height of the waveguide. And this condition is must. When we calculate R, which is a ratio of small h by capital H, it has to be somewhere between 0.5 to 0.9 so that it supports the fundamental mode. Okay. So we need to choose the dimension such that it satisfies this Sorev's equation. And not only that, it also allows us to have a shallow type of etching. I mean, shallow type of etching is possible because that is actually easier also. And then these type of waveguides can be fabricated. So what is this grating on the rib structure? The grating waveguide structure here mainly composed of three layers: a grating layer, a waveguide layer, and then a substrate. So when the light is launched into the core, a portion of the light is transmitted here directly, while some portion of the light is coupled and reflected back, and it is confined in the core. Structures are known as surface grating structures. The reason because they are created by removing the substrate through an etching process. And they also allow for larger coupling coefficient. I mean, the amount of light confined in the core is more and it stays there for a longer time. So this is a structure of the rib waveguide. You can see here we have a lower cladding SiO2, and on top of that we have a silicon core. And small h is a slab height, capital H is the total height, or I can say the thickness of the rib waveguide, and W is the width of the rib waveguide. And this particular, the either side, it is known as H depth. So whenever you are designing a waveguide grating device, it's not only important to choose the grating period. At the same time, it is also necessary to wisely choose the width, the height value, and the ratio R, so that our devices is having minimal losses. This is a single mode profile of the rib waveguide. Here I have chosen the dimension in such a way that the condition R is between 0.5 to 0.9. And see, this is a modal profile where clearly you can see the fundamental mode which is there in the core region. So this is one such type of device where on the rib we have made the gratings. Here, as I said, to satisfy the Sorof's condition, the dimensions of the device I have taken was total height was 280 nanometers. One more important thing, whenever we are choosing the slab height or maybe the total height of the waveguide, randomly we cannot take the values, because we have to follow certain conditions like what are the wafers available during fabrication, because everything is a CMOS based fabrication step. So what are the standard wafers available? Keeping them in mind, we have to choose our dimensions. So here the total device height I selected around 280 nanometer with a width of 500 nanometer. Along with that, the grating period. This grating period is selected by solving certain equations here. I mean, you have to satisfy that grating principle. Okay, so based on that, we have selected this grating period, and the operating wavelength was around 1550 nanometers, because that is the usual C band which we choose, and the grating depth was around 60 nanometers. So you can see here the top view of the device. We have a SiO2 layer. On top of that, we have a silicon core, and on top of that, we have etched the gratings. And this is just the front view of the device. And this particular picture, it shows the various, I can say, the steps required to fabricate these type of devices. See, it is not, all of us know that it is not that easier to fabricate these devices. So of course, we have certain tool like IntelliSuite. By taking that IntelliSuite help, you can know how your devices can be fabricated and what are the various steps it has to undergo. So here I have just tried to show the glimpse of the fabrication step for these type of devices. You can see here we have one silicon layer, the bottommost layer. It's a silicon layer of 1 micrometer thickness. And on top of that, we have this box layer, that is buried oxide layer, which we have taken around 2 micrometer. And on top of this box layer, we have the top silicon layer, where the thickness of the silicon layer is around 280 nanometer. And now we have to make a rib structure. We need to remove the unwanted silicon on either side. To do that, initially we have deposited, you can see this yellow color, a photoresist mask, which is around 220 nanometer thick. The photoresist name is PRAZ5214. On the top layer of the silicon, using a step known as a spin coating technique or method. Now, using UV lithography technique, the top layer is exposed to UV light, and then slowly the photoresist is removed from the other region, keeping the rib part intact. And now to etch again the unwanted silica and the photoresist, we have used material like PRAZ5214, which is also type of photoresist, using reactive ion etching method. So like this, using IntelliSuite tool, you can know what are the various steps which will be involved when you want to go with the fabrication. Because when you are making papers and when you want to submit your papers, the editor will be looking what is the new thing which you have done in your work. So I think people can design on the various platform like console or maybe Beamprop or maybe Lumerical, and then using this IntelliSuite tool, they can have a glimpse of the fabrication procedure. So these are the performance metrics of the device which we had designed. Here, to know whether our device is responding or not, we had taken the refractive index between 1.32 to 1.33. So you can see clearly the transmission spectrum for two different analytes with a refractive index of 1.32 and 1.33. So whatever dimension I had showed earlier, they were freeze as it is. Only the different wavelength, I mean different refractive index we have considered here. So you can see two different peaks here for different RI. So this is another performance metrics where we have varied the geometry of the device and seen what kind of impact it has on the sensitivity of the device. We have taken the duty cycle to be around 50% because this parameter is very, very essential. If I want to have a maximum coupling efficiency, we have to design a grating such that it has a duty cycle of 50%. And now see the first diagram and the second diagram. For different rib width, what is its impact or the effect on the sensitivity we have calculated. So you can see here, as we are varying the rib width, the sensitivity is also increasing. It's very obvious because wider the rib, the light, it is staying for a longer time. So it is able to interact with the analyte for a long duration. So obviously the sensitivity comes up. This is what you can observe in this graph. The second graph, it is with respect to the grating depth and again sensitivity. So here what we observe that initially when we change the grating depth, our sensitivity improved slightly. And the moment we start going towards higher grating depth, the sensitivity reduced. So these are two performance metrics of the device. And along with that, we had also varied the grating period and seen whether the wavelength shift is happening or not. And the second diagram, it is showing the transmission spectrum, I can say, for different analytes. Because initially we had just taken one or two refractive index, 1.32 and 1.33. With that, we just saw the performance metrics of the device by changing the dimensions. Later, different types of analytes we considered and we checked whether our devices were responding or not. So here, even with the grating period, there was a more shift in the wavelength. This is obvious because of the grating principle. And once we did all the simulation, we have done plotting of the graph. Next was to calculate important parameters like sensitivity, figure of merit, FWHM, where the sensitivity, here we have calculated bulk sensitivity, because again, when you are calculating sensitivity, it can be a bulk sensitivity or surface sensitivity. So in the later slides, I'll show you what is the difference here, where the bulk sensitivity is mainly given by the ratio of shift in the wavelength, or I can say the change in the wavelength due to the change in the effective index. Similarly, full width half maxima, which is basically obtained from the resonance peak, it is given by the ratio of the resonance peak, the maximum peak value divided by lambda 3 dB down. And apart from these two, sensitivity and FWHM, figure of merit is also a very important parameter to know the performance of our devices, which is again given by the sensitivity by FWHM. Then we have another important parameter, which is intrinsic limit of detection, which is nothing but the minimum detectable refractive index change of the device, which is again given by FWHM by the sensitivity. It is just inverse to figure of merit of the device. So these are the performance metrics of the device which we had designed, where we obtained the bulk sensitivity around 770 nanometer compared to the base paper which we had considered, where we got FWHM was around 7.5 nanometer. You can see the footprint area, it's around 12.5 micrometer square, is very small. And even the limit of detection which we achieved was 9.7 into 10 power minus 3. Of course, compared to the articles which are there in the literature review, whatever the limit of detection which we achieved was little lesser compared to the other paper. So of course, different way you can optimize the device dimension, different way you can consider to improve this limit of detection. So this is another structure. So one group from IIT Indore, they had done on this, where this is one waveguide structure. where there is a center cavity and either side they have created the gratings. So the below picture you can see how during fabrication the gratings are made. So this is one type of device where on the same waveguide you can have multiple gratings. This is useful for multi-sensing parameters. And this is another type of grating based device. You can see here, this is a slot waveguide. In the sense we have this one substrate, on top of that we have a silicon, and then there are two slots here. Okay, and top of the slots they have made the gratings. This particular group, one more thing they have done here, one major I can say achievement, they have coated with a gold layer here. You can see this yellow color here, it's a gold layer, because gold has a very good property of reflecting back the light. Okay, so that for the light to stay for a longer time in this grating when it is interacting with the analyte, for that purpose they have coated with the gold layer here. So you can just see the front view of the device, and they have coated with the analyte here. And this is a profile, the model profile of this slot waveguide. You can see the light is confined between the two slots. So this is their front view, and this particular blue color picture, it is showing how the light is propagating through the gratings which are based on the slot. And they have measured the transmission spectrum with gold layer coating and without gold layer coating. And at the same time, they have coated here with TiO2 layer, because they have not done bulk sensing, they have done the surface sensing. Okay, for that they have coated with TiO2 layer. On top of that, they are placing the analyte, and they have calculated what is the response with and without coating of these materials. And they have taken once again two types of refractive index for different analytes, 1.35 and 1.37, where they are trying to calculate how much FWHM they are able to achieve with respect to 1.35 and 1.37 refractive index value. And this is a transmission spectrum for different types of analytes they have plotted. So it's a direct relation. You can see the obvious shift in the wavelength or the power. So this is another group where they have made the gratings on the polymer based waveguide. You can see earlier we had SiO2, on top of that we had silicon layer. Now they have taken the bottom layer as polymer epoxy, and then on top we have the silicon. And then on top of the silicon, they have put the sample. So you can clearly see here, the first picture is with respect to the bulk sensing. The second one is with respect to the surface sensing. The difference here is that in case of bulk sensing, the device is immersed in the analyte. Complete analyte, you can see it's coming and sitting here. Whereas in the surface sensing, only on the grating part, they are placing the samples. Okay. So again, it's left to the people like scholars, whether they want to go and check for the bulk sensing, or maybe they want to have a dimension with respect to the surface sensing. Accordingly, they can decide here. So once again, the light is launched and reflected light is responded, I mean, is collected, that reflected light parameter. And with that, they're able to calculate the sensitivity and other values. So this is the response. Here it is the plot of wavelength versus transmission power. You can see with respect to different RI value, they are getting different transmission spectrum. The first diagram is with respect to the bulk sensing, and the second one is with respect to the surface sensing. So again, like it depends whether you are looking for bulk or surface sensing. Accordingly, you have to choose your sensing way. So this is one more work where we have also coated this gold layer just below the this one grating. These gratings are made on the rib structure. Earlier, I had showed you the slot waveguide. I can see here. This is a slot type of waveguide where we have two kind of ribs here. On top of that, they had made the gratings. Similar to that, we have made this device where we have this bottom SiO2 and top SiO2, in between again a gold layer, because the gold has a very good property of reflecting the light back. And then on top of this top silicon layer, the gratings are made. So here once again, you can see by wearing the gold layer thickness, how how it is, what kind of impact it has on the wavelength shift. So this is a modal profile where the device dimensions are taken in such a way that it is supporting the fundamental mode. And this graph you can see, as the gold layer thickness we are varying, there will be a shift in the wavelength. And initially up to 40 nanometer, it was increasing, later it came down. And for different refractive index, this is a transmission spectrum where we have compared our sensitivity with the earlier reported sensor. So you can see here the proposed sensor, whatever we have proposed with the RIB waveguide, we achieved a sensitivity of 1160 nanometer, and the footprint area was remained 12.25 micrometers square. Okay, so we have just given the comparison with respect to the previously reported sensor, and overall the sensitivity has improved here with reduction in the footprint area. Now, coming to the fiber brag grating, as I said, we can have waveguide based grating devices or maybe fiber based grating devices. The one demerits of fiber brag grating, if I want to have a lab on chip kind of application, I cannot go with fiber because of the size. So that's why we can focus on waveguide based of devices. But if I want to have some physical sensor, I want to do certain biomechanical or any type of temperature, vibration, or pressure sensing, fiber brag grating are the ideal devices, I can say. So once again, the working principle remains the same, where we have inner core and the outer cladding, where when the light is launched into the core of the fiber, the gratings are created here. So most of the wavelengths are getting transmitted. Some of the wavelengths whose period is in phase with the grating period, they are coupled and reflected back. So you can see this transmission and reflection spectrum. Some of the wavelengths are transmitted and some of the wavelengths are reflected back with a stronger coupling. And the distance between the two gratings is known as the pitch or the grating period. So this is one way how the gratings are created on the fiber. You can see there is a fiber here. On top of the fiber, a face mask is kept, and on top of that, there is a UV light which is made to fall on the fiber. Through these photomasks, a certain portion of the fiber, it is exposed to UV light, and certain portion is not exposed to UV light. So when it is exposed to UV light, there will be a change in the effective index. So the total effective index which is available in the grating region is known as effective index of the fiber. And this effective index is directly related to the grating, the Bragg's wavelength. You can see Bragg's wavelength equal to twice the N effective into grating period. So whether there is a change in the N effective or there is a change in the grating period, it has a direct relation in the Bragg's wavelength. So if N effective changes, similarly lambda B changes. If grating pitch also changes, similarly lambda B also changes. And now coming to their application, there are various different parts of the body you can use these sensors to capture, okay, or to measure various parameters, like we can measure the blood pressure, the heart rate, EG, ECG, or heart, the oxygen saturation level. Different parameters can be measured with the help of these type of sensing devices. So different groups, they have worked on different types of sensing application. Some of the groups I'm showing here. This is one such group where they have made use of fiber grating device to know the plantar pressure. So you can see just below the feet, they have placed three sensors here. This is array of sensors in the sense in one optical fiber, three different places they have created the gratings. Similarly, on the other side also, array of sensors have been placed. Okay. So with this, when a person is made to stand on this platform, his weight is falling on the platform. Along with that, there are specific pressure points. You can see here, there are specific pressure points. The moment a person stands, his weight is falling on the platform, and that is transferred to the sensor. As a result, there will be a shift in the grating pitch, so which will directly make a shift in the Bragg's wavelength. So depending upon the amount of wavelength shift, we are able to identify what is the pressure exerted on this point or this point or this point. Like this data can be collected, and doctors is able to know that whether the person is having any issue with the limbs, or whether the person is diabetic or not, or even for gait analysis, these type of sensors can be used. even to know whether a person is having gangrene or not. Looking at the pressure values, easily it is possible for the doctor to identify the various problem associated with the person's feet. So this is one more example where they have used FPG based probe in order to capture or measure the carotid arterial pulse. You can see here the device is here, and just below this on the flat portion of the device they have placed the sensor. You can see this lady, she has kept this device on that uh, pulse, I mean on the nerve, and then those parameters it is made to fall on the device where the FBG is embedded, and simultaneously they are recording the response of the sensors. So with respect to the time, the amount of strain which is exerted on the fiber that can be recorded, here in this case they have taken 4 different subjects and they have recorded their arterial pulse. So once again it helps the doctors to know what kind of issue the person is having. So this is another example where they have used FBG based plethysmography device to know the or to acquire the arterial pulse. You can see here in between these 2 fingers there is a fiber and somewhere in middle there is a grating. So when the person is moving his fingers or is made to change that finger location, I mean movement basically, there will be a response captured by the sensors. So that is again they have plotted here, and they are trying to show that again these type of sensors can be used to acquire these type of data. So this is one more example to know the bite force measurement, because whenever people want to go and have some kind of surgery, tooth surgery, or the complete set they want to have it, then again these type of sensor can be used to make a bite force measurement device. So you can see this is the setup where they have placed the FPG sensor, and this lady is holding that setup, I mean that device, and she's exerting the force. Okay, based on the amount of force she is able to exert, there will be a shift in the wavelength, and that is again captured, and it is possible for doctor to give the proper treatment procedure. So this is another application where they have used FDG sensor to measure the angle, joint angle, this one data. So this type of devices are known as goniometers, or also known as range of motion type of devices. So here the sensor is placed on this elbow part, on the ankle part. Based on the amount of movement she is able to move, the sensor is giving us the response. And again, this data will help in case if person is having some injury, or maybe he wants to undergo some physiotherapy procedure or sessions. So this type of data helps the doctors to give a proper treatment. And now coming to one important application of fiber grating sensor, which is known as a hand grip device. So hand grip device, I can say from this we are able to know the muscle movement, or how much amount of pressure the person is able to exert. This type of data can be collected, and it will help again the physiotherapist or the physician to suggest suitable exercises in case the person had any injury or fracture, or maybe any type of issue associated with his wrist that can be known. Those from the values the person will get, I mean the doctor will get to know what kind of physiotherapy exercises I can suggest them. Otherwise, if the person is having some surgery, post surgery, whether there is a healing of the bone happening or not, that is all can be possible to know. So here, initially to design the device, we have gone with the 3D printing, where we have made use of ANSYS simulation tool to design the device and to know whether that exactly which place we need to place the sensor, so that when the person is holding the device, maximum pressure he is able to exert on the device. So I'll just show you the device. So this is the one on the CAD tool. We had done this designing, where this is showing the ANSYS strain stress analysis values. So when we designed, we came up with the 5 grooves here. I mean, you can see the grooves here, where the person is made to keep his fingers and then exert the pressure. So this is a device we are having, where we have embedded 2 FPGs here. You can see this device is made up of aluminum because of the properties of the aluminum material. and we have inserted two FDG sensors, and also we have given some protective packaging here for these sensors because they are so brittle, it is easily breakable. So we have to protect them with certain packaging technique. So this is a complete setup. You can see the device is kept here where we have two sensors, FPG1 and FPG2. They are connected to the interrogator. And when the person is holding this device and exerting the pressure, applying the force, I can say, there will be a shift in the wavelength, and that can be noted down on the this monitor. So now, to prove that our developed device was very good, it can be used for physiotherapy application. We had taken different case studies. So this is one method of knowing the muscle activity. If a doctor wants to know whether there is a person is able to exert the force or not, whether the person is able to make a movement of his fingers, they usually place the EMG electrodes and they try to capture a data like this. Based on these type of data, he is able to say, okay, you're having this issue, probably you have to undergo this physiotherapy session. So we just wanted to prove that rather than going with the conventional EMG, because what happens in the EMG, if these electrodes are not placed exactly on the required muscle, chances of that getting a error data. Even doctors sometimes not possible to know what exactly is the issue or why much muscle movement is not happening. So this was one demerit with the existing EMG. So we thought of coming up with our device where it is non-invasive and it is safe also. Even children, all elderly people, they can easily hold it and they can know what is their grip force. So this is one that comparison experiment which we did. Here you can see we have placed the EMG electrodes and the person is holding the device. So with the help of these electrodes, we are noting down the response, muscle response. And even at the same time, the person is holding the device and putting the pressure. He's applying the maximum grip force. And then we are collecting the data. So you can see here, the response which we got with EMG was almost similar similar to the response which we got it with the fiber grating based device. You can see here both for the right as well as for the left hand, we had noted down the waveform. And the second graph, it is showing the response of fiber grating based device as well as the standard EMG method, where for different positions of the hand, I mean the wrist can be kept in normal position or maybe it can be in the extended or maybe in the flexion posture. The type of response we got it for EMG, almost the responses were matching with respect to the fiber grating based device. So you can see this is a normal position, the flexion and extension, both with respect to left hand and right hand, we had noted the response. Almost they are matching. So when we consulted a physiotherapist, they said, yeah, almost the results are matching. So probably in the coming days, these EMG methods can be replaced with this optical based hand grip devices. So this is the responses which we got it for the EMG and FBG based device. You can see here, we have considered three different subjects, both for the left as well as for the right hand, and different position of the wrist, normal, flexion and extension. We had noted the response. So with respect to EMG, since it is an electronic based method, we noted the response in microvolt, and FBG, it will be a shift in the wavelength. Later, with the calibration value, we converted the amount of shift to a kilogram. So basically what happened when we approached the physiotherapist, he wanted to know the data in terms of graphical representation, because doctors say that like how ECG waveform helps the doctor to know, to identify whether the person is having some problem related to his heart. The similar way they wanted to have some graphical way of see the I can say the movement of the hand, or maybe how much the person is able to exert the force. So all these data help them to know whether the person is able to put more pressure or not in case of any type of injury. Apart from that, we also did one more experiment with the same device where we calculated the dominant and non-dominant force values both for male and female. You can see the first diagram here. It is the response of time versus the hand grip device. So we have classified them into three different parts. You can see the rise time, the grip holding time, and the fall time. So what is this here? That rise time, we made the person to sit, relax. He should not be under influence of any medicine or alcohol. He has to sit relaxed, and then he has to hold the device and start applying the force. The moment he start applying the force, you can see gradually the force is increasing. I mean, there is a more shift in the wavelength. Then grip holding time, he is holding the device, maximum pressure is exerting. So that duration is the grip holding time. And then falling time, slowly the person is made to release the applied pressure on the device. So three different cases, three different time slots we have noted down: rising time, falling time, and the grip holding time. And the second graph, it is showing the mean variation of the hand grip force, both with respect to male and female participant, as well as the dominant. Dominant means the right hand, non-dominant is the left hand. So all these data, when we captured and we kept, it's very helpful for clinical studies for the patient and for the doctors. So these are the recorded values from the device, where again, as I said, using a calibration value, we converted the shift in the wavelength to kilogram. So this is another experiment where three different position, the person is holding the device and they are exerting the force. And again, we plotted them in graphical way so that it is easier for the doctor to know whether the person is having some issue or not. So both for left and right, male and female subject we considered, and we did the plotting. So again, these are the discrete values which we calculated and we have mentioned here. So this is one more interesting case where we wanted to show that this device is versatile. It can be used for any type of patient. This person had a fracture actually in his hand. He met with an accident. He had fracture, where the usual procedure is doctors, they advise them to go for the X-ray every 3 weeks or 2 weeks, and based on the hello.
அம்மா நான் தான் பேசுறேன். அமுதாக்கு நான் கால் பண்றதெல்லாம் உங்களுக்கு பண்ணிட்டேன்.
Hello. Okay. So we can see the X-ray images here. Usually the procedure is doctors advises them to go and take X-ray. They come with the X-ray report. Doctors, he observes the X-ray and then he's able to say, yes, there is a healing is there in your bone. Probably this exercise or maybe this medication you can take. The one problem here is that if a person is having such type of injury and multiple times if he has to undergo X-ray session, then you can imagine how much he is exposed to the radiation, because all of us know fraction of 5-minute radiation exposure, how many healthy cells are killed. So we wanted to prove that rather than going with the traditional method of multiple times X-ray session, probably the person can hold this hand grip device and he is able to apply the force. Based on the applied force, there will be a corresponding shift in the wavelength, and from there we are get to know how much amount of force he is able to put. So looking at those values, it is easier for the doctor to know, yes, the person is getting healed, maybe the bone is healing, probably this type of exercise they can do, or maybe this type of medication they can do. So that was a major intention here. So you see, these are the graph where immediately after the surgery, after 2 weeks, doctor had asked him to go undergo for X-ray session, and at the same time we made the person to hold our device and noted the response. Second stage, again after 2 weeks, again after 2 weeks, like this we had a gap of 2 to 3 weeks every time during this entire procedure, and we noted the response. Ultimately stage 4, that is almost after 3 months, the person was able to apply maximum force on the device. And this is just a comparison, like looking merely at the X-ray, doctor was able to say, yes, it is healing, there is slight improvement, there's a slight change. So with that assumptions, we had plotted even our data of FBG based device, and we are able to show that almost like what was possible to tell with the help of X-ray, it is also possible to tell with the help of a hand grip device. So these were the data which we plotted for this fractured arm. And since we had association with MS Ramaya Hospital, we had gone to the hospital, and luckily we we got many patients because this IAC had an MOU with MS Ramaya. So they helped us with the patient and we could capture a lot of data. So it's not only for biomechanical application, even this fiber Bragg grating sensor can be used for many other application. Nowadays, we have heard of wearable sensors and smart textiles. You can see here inside this textile, this cloth, they have embedded the sensor. For example, if there is an elderly person, maybe 70 or 80 years, and he has to stay alone in the home. So probably these type of textile clothing with the wearable sensors can be made when the person is wearing such clothing, when even though nobody is there at home, his temperature or maybe his heart rate, all this parameter with the help of these FBG devices can be captured, and maybe they can be monitored on a laptop or a mobile elsewhere. So we are able to keep a monitoring of the elderly people. Not only that, even in ICU, people who are in coma or undergone a major surgery, even in ICU, it is possible to monitor their vital parameters when we make the patient to wear such type of textiles or clothing. Okay. So these are some of the domain, I can say, area where students can work on the project. It's not only students of UG and PG, even scholars can do a lot of things, because even a slight change in the sensitivity value or maybe some kind of changes or betterment if we do with these type of sensors, obviously it is recognized and we are able to publish even good papers in good journals. So people who are interested, they can give small work on these devices to students. And to work on these sensors, simulation based, we have various tools like RSOF, COMSOL, and Lumerical tool. So they are available for 1 month usage. I mean, you have to go to their website, you have to register with your college ID. Then for 1 month, they will give you the student version where you can install it and you can use it. And not only these GUI based tool, even with MATLAB, it is possible to know the basic performance parametric of these type of sensors. So these are the references which referred while making these PPTs. Okay. So with this, I think I'll conclude with my session. Hello.
Yes, ma'am.
Uh,
Participants, if you have any queries, you can ask with madam.
So any participant who want to collaborate with Ibrar madam, she is ready for that also. Correct, Ibrar madam?
yes, ma'am. Yes.
Because this is the opportunity, this is the time when people can collaborate and they can exchange their idea and they can make the joint paper.
Yes, ma'am. Because that is the demand of the day.
Yes.
Especially colleges and all, they are saying do collaborative work, do collaborative publication, bring collaborative research funding. So people who are interested, definitely they can collaborate.
Yeah. So anyone is not having any question, then I will ask one question.
Yes, ma'am.
Okay. So what happened? Your most of the work is related to the fiber crack rating.
Hmm.
So what I was thinking, interrogator and all you will get nowadays. iSTEM is also one of the this one through
Hmm.
that or anyone many places. Interrogator Chetana is also having. So interrogator
Yes,
you
yes.
will get. But
Hmm.
my question is
Hmm.
how to protect the fiber, because what happened fiber bracketting, because what it is very fragile in nature,
Yes,
and
yes.
one optical fiber uh, sensor, grating sensor, cost a minimum 15
Correct,
minimum
ma'am. Hmm. Hmm.
15,000 to 30,000. So any idea do you have about protecting the fiber, how to cushion
Ma'am,
it?
usually, yeah, yeah. See, if I'm going with the temperature monitoring and all, even steel, small steel pipes are available, or maybe this copper pipes. The grating part can be inserted inside that, and it is protective. And at the same time, the sensitivity is also not reducing. It is able to give the response. That is what I have seen with respect to temperature. Even pressure value, if I'm using as a, pressure sensor, it can be encapsulated with aluminum, because aluminum is the best material, I feel. And at the same time, even
Yes.
the sensitivity is not getting compromised.
Thank you. So, if and no question in chat box, you check. Organizer, can you check in chat box?
They're asking contact details of madam.
Okay. So, Ibrar, you can give the contact detail.
Yes, ma'am. I'll stop sharing this.
Yeah. After that, in formal way, you can end the session if no question is there.
Participants, if you have any questions, you can ask now, or you can put it in chat box. I think no questions, ma'am. No other questions. Your contact details they're asking. Uh,
Ma'am, shall I give it to you, or shall I give to Prita, ma'am?
you can give to Preeta, ma'am. We'll put in that WhatsApp group.
Okay. I think
Definitely, ma'am.
chat box. Can you able to write Ibrar in chat
Mm,
box?
yes, ma'am. I think, yeah.
Just you write. So maybe some of the participant want to interact with you.
Hmm.
So kindly help them. Like this, actually, I got lot of contact because
Correct,
I
correct,
keep giving many talks. So people will interact, and so we are making paper. So number of papers will be more actually, and we
correct,
our
ma'am.
knowledge will enhance also.
Correct, correct.
So whenever you are free, you
Yes, ma'am.
can help. So
Definitely, definitely.
I what I was asking, evening time or sometime, suppose if from our faculty, some people they are interested to work with you, just to
Yeah.
learn the art soft or
Mhm.
just to work on the biomedical healthcare devices. So will you able to help them?
Definitely, ma'am. Definitely.
Okay. According to your time, they will plan, and so that.
Sure, sure,
Thank you. I'm
sure.
very much, very, very, very. I'm thankful to you for your
Ma'am,
nice
first of all,
presentation.
thank you to you for giving me such a very good opportunity. Who will get the opportunity to talk at the international level FDP? Thanks a lot.
Very nice. And I'm happy that you are interested to collaborate. So some few faculty from our college are very interested and highly impressed by the work you have done, real time work, especially for the X-ray and all you were showing.
Yeah,
So they are very yeah, they are very interested. So they want to work in that because rest of the components we are having, all
yeah.
interrogator and FBG sensor, the real time. So they want to learn from you the basic R soft,
Hmm.
basic fundamentals, so that she can go further.
Definitely,
My
definitely.
nowadays my attention is only for the protecting the FBG because I lost many
FDP, yeah.
FBG. So okay,
I think
thank you.
in Kenya itself, they have some setup, ma'am, where they give this protective layer on the grating.
Then we
I
have to go there.
I think I'll get somebody had informed me if I'm going there, because now our project is going on, where again we are
Uh,
making use of FDG sensors. So we have to go for
yeah,
the coating of the
for
protective
that 10
layer.
lakh funding, na? Yeah.
Yeah, yeah, for 10 lakh funding. So we have finished with all simulation work by now. Probably next month onwards, we have placed the order for the other setup and all. It's going to come by May first week, I guess. And then we'll be starting the work.
Kindly share that contact with me
Hmm.
so that I
Definitely.
can approach for protection of the FBG I want.
FPG sensor. Yeah, ma'am.
Thank you.
Okay.
Thank you very much.
Thank you so much, ma'am.
So,
Thank you.
organizer,
Thank you to all the
thank
coordinators.
Yes, ma'am.
organizer, please,
Yes,
in
ma'am.
formal way, can you end the session?
Yes, ma'am. On behalf of the Oxford College of Engineering and all the participants present here, I extend a heartfelt thanks to Dr. Ibra Jahan ma'am for the informative talk on grating structures for biosensing applications. We are grateful for the knowledge and expertise you have brought to this discussion. We thank you for the time and effort you have dedicated to share your thoughts with us. Thank you once again for the informative talk, ma'am. Thank you.
Thank you so much, ma'am.
I will tell if all are there, we can take one photograph if they can on the camera. Resna? They're not there.
I think they all left.
They are
No,
left.
no, they are switching
Okay.
on. They are switching on.
Okay. Few photographs we need actually. Yeah. Thank you. Few people just on the photograph because when we'll put in the Government of India Gyan portal, na, it will look nice. You all on the camera. No issue. Yeah, few photographs you take Resna.
Yes.
And I'm able to see the participant also. You all are from outside? Where you all are? Kindly tell. And Nahiba, Supriya, from where you are?
And we are from Hassan. I'm from Hassan, Supriyanand.
Okay.
Ma'am,
And
I am
then
from Chennai
Valar,
Institute of Technology.
you are from?
Chennai Institute of Technology, ma'am.
Okay. And Valarmati? Valarmati is from where? Usha.
Yes, ma'am. I'm a research scholar from Anna University.
Anna University. Okay. Nice to see all of you. This is the time when we are interacting and seeing. So thank you so much. Okay, some few people can on the camera. Rupa, Dr. Rupa, Chitra, Rekha Reddy. I'm very happy across the India people are joining. Last day at valedictory function, kindly all of you should be there, okay? So that my principal will join and give your feedback. Okay? Thank you, very nice. I will maintain database also, so that in future also anything we can collaborate. And we will ask, and you can introduce Dr. Jitender from where you are. I am seeing you always, you are attending. You have to unmute, sir. No, I can't hear you anything. Dr. Jitender?
Good morning, ma'am. Can you hear me?
Yeah, now I can hear you.
Okay, good morning, ma'am. I am from Chandigarh University, ma'am.
Oh, Chandigarh University. Oh, so nice. From Chennai, Chandigarh. And B. Kishore.
Yes, ma'am. Yes, ma'am.
Kishore. Sir, from where you are? You have to unmute yourself. No, I can't hear you anything. You have to unmute. This type of internet glitches will be there whenever we will do online anything. We have to bear that. No, I can't hear anything. B. Kishore. I think you have to. Yeah, you have to unmute. You are muted yourself. I think organizer, you are. I think she has not muted. You have to unmute. No issue. We will see at the time of valedictory. Okay. Thank you.
Yes,
Thank you so much. Thank you. Thank you. Okay. Now we'll meet by 2 afternoon, 2 o'clock.